In this video, I would like to discuss about the molecular orbitals in boron, carbon and nitrogen molecules. In the previous video, we discussed about the molecular orbitals in oxygen, fluorine and neon molecules. Now, in case of boron, carbon and nitrogen molecule, as the atomic number of boron is 5, carbon is 6 and nitrogen is 7. They have total 10, 12 and 14 electrons respectively. It means boron is having total 10 electrons, carbon is having 12 electrons and nitrogen is having 14 electrons. On the basis of the molecular orbital diagram of oxygen molecule, boron molecule can be predicted, and the boron molecule is dimagnetic. If you see the electronic configuration of the boron molecule, then it is K sigma 2s2, sigma star 2s2, sigma 2pz2. So in the sigma 2pz bonding molecular orbital, the two electrons are paired, and carbon molecule is having the electronic configuration K sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px1 and pi 2py1. It means that it is paramagnetic. But experimental evidences shows that boron and carbon molecule are paramagnetic and dimagnetic respectively. According to the hemodiagram of the O2 molecule, we can predict the boron molecule is supposed to be dimagnetic. And that is true. But actual fact is that the boron molecule is paramagnetic and carbon molecule is diamagnetic. So how this will be happen? And also spectroscopic studies shows that in boron and carbon molecule, sigma 2pz molecular orbital is higher in energy than pi 2px and pi 2py molecular orbital. As we see the hemodiagram of the oxygen molecule, you can see here in this hemodiagram, as sigma 2pz bonding molecular orbital, it is having lower energy than pi 2px and pi 2py. So usually the electrons can be entered into the sigma 2pz. For example, in case of the boron molecule, what happens? Boron molecule, there are total 10 electrons. Out of that 10 electrons, 4 goes into the non-bonding. Now 6 electrons we have to fill. So sigma 2s2, sigma star 2s2 and sigma 2pz2. So it means that it is diamagnetic. But experimental evidences shows that boron molecule is paramagnetic. It means that this hemodiagram could not explain the properties of the boron molecule correctly. Similarly, in case of the C2 molecule, C2 molecule is having total 12 electrons. So sigma 2s2, sigma star 2s having 2 electrons, then sigma 2pz, and in this there is a 1 electron. Okay, in case of the C2 molecule, it means it is paramagnetic. But experimental evidence shows that C2 molecule is not paramagnetic, it is diamagnetic. So how it becomes happens? Why boron molecule it is dimagnetic? Boron molecule is paramagnetic and carbon molecule is diamagnetic. So there should be some mixing of atomic orbitals. And this can be explained on the basis of mixing of atomic orbitals, mixing of 2s and 2pz atomic orbitals in case of boron, carbon and nitrogen molecule. You have to remember that such type of the mixing is not possible in oxygen molecule, in fluorine molecule and in neon molecule. In the MO diagram of these molecules, always sigma 2pz, it is having the lower energy level. But spectroscopic evidences shows that in case of boron and carbon molecule, the sigma 2pz molecular orbital, it is higher in energy. So this is totally unusual. So let us explain this now, how the sigma 2pz molecular orbital is having the higher energy and how the boron molecule is paramagnetic and carbon molecule is diamagnetic. So this can be explained on the basis of mixing of atomic orbitals. We know that sigma 2s and sigma star 2s molecular orbitals are formed by the combination of two 2s atomic orbitals of the two atoms. It means when the two 2s atomic orbitals get overlap. Suppose 2s atomic orbital of boron get overlap with 2s atomic orbital of boron, there is a formation of sigma 2s and sigma star 2s, bonding and anti-bonding molecular orbitals. Similarly, sigma 2pz and sigma star 2pz molecular orbitals are formed when two 2pz or atomic orbitals of the two atoms get combined. However, if the energy difference between the 2s and 2p atomic orbitals of an atom is small, in some atoms this energy difference is small. The energy difference between the 2s and 2p atomic orbitals, the energy difference between 2s and 2p atomic orbitals, if this difference is small, there is a possibility of mixing of 2s and 2pz atomic orbitals. There is a possibility of mixing of 2s and 2pz orbital. Such type of the mixing, it is not possible in case of oxygen fluorine molecule, but this type of the mixing is possible in case of the boron, carbon and nitrogen molecule. Because in case of these orbitals, the energy difference between the 2s and 2p atomic orbital is very small. This table shows in boron molecule it is around only 449 kilojoule per mole. In case of the carbon molecule it is 510. In nitrogen molecule it is 570. Means this energy gap between the 2s and 2p orbital. And if you see in case of the oxygen it is very high, 1430. So as this energy gap will be higher in case of the oxygen atom, no mixing will be here. It means that there is a sufficient energy gap between the 2s and 2p atomic orbital. So in case of the boron, carbon and nitrogen atom, as this energy gap is very, very small, the mixing of atomic orbital is takes place. Which atomic orbitals get mixed up? The 2s and 2pz orbital. These atomic orbitals can be mixed up and the molecular orbitals are changed due to this. The energy level of the molecular orbitals can be changed. So I would like to show this on the other screen. You can see here. The mixing of the atomic orbital, it is takes place in case of the boron, carbon and nitrogen molecule. This is because the energy gap between the 2s and 2p atomic orbital, it is very small in case of these molecules. So as these two atomic orbitals are very close to each other, hence the mixing of 2s and 2pz, both these atomic orbitals are suitable for the formation of the sigma molecular orbitals and sigma bond. So mixing of these orbitals will be takes place. This is similar to that of the hybridization. So before the formation of the molecular orbitals, these atomic orbitals can be combined, and due to this the energy of the molecular orbitals will be changed. So this is the new thing in case of boron, carbon and nitrogen molecule. This is not happen in case of the oxygen molecule, in case of the fluorine molecule, because in case of oxygen molecule, this energy gap is very large. It is around 1413. So therefore, no mixing will be takes place there. So before the formation of the molecular orbitals, first of all, these atomic orbitals can be mixed up. Means 2s atomic orbital can be mixed up with 2pz atomic orbital. This is very similar to the hybridization concept. And due to this mixing, what happens? Because this is the strong overlapping. Due to this mixing, what happens? The molecular orbitals which are formed because of due to this, that is sigma 2s and sigma star 2s, then sigma 2pz and sigma star 2pz. So these sigma 2s and sigma star 2s bonding and anti-bonding, these molecular orbitals get lowered. Their energy becomes decreases. While the sigma 2pz and sigma star 2pz, these molecular orbitals have increased in energy level. This is the new change that will be takes place in case of boron, carbon and nitrogen molecule. Now in this mixing, the 2px and 2py orbital do not take part. Therefore, their energies does not change. That molecular orbitals remains unchanged. Okay. So this is the new change, and the relative order of the energy of these molecular orbitals now in this way. Sigma 2s is lower than sigma star 1s, sigma 1s, then sigma star 1s, then sigma 2s, sigma star 2s. Now pi 2px and pi 2py come first, then sigma 2pz. In case of oxygen molecules, sigma 2pz come first, then this pi 2px and pi 2py. But in case of boron, carbon and nitrogen molecule, due to the mixing of the atomic orbitals, as some molecular orbitals get lower in energy level and some molecular orbitals having the higher energy level, so the energy level of these molecular orbitals get lowered, and energy level of sigma 2pz and sigma star 2pz molecular orbitals have rise in energy level, but the pi 2px and pi 2py does not change. So this is the new change, and I would like to show this new change in the molecular orbital diagram of these molecules. So let us see first the molecular orbital diagram of boron molecule. So you can see here the molecular orbital diagram of the boron molecule, and that new change can be seen here. So as we know, the atomic orbitals of the boron onto the left hand side, atomic orbitals of the boron onto the right hand side. First of all, 1s, 2s, 2p. Let us write here the electronic configuration of the boron atom. Boron is having atomic number 5, having the electronic configuration 1s2, 2s2, 2p1. Okay, 3 valence electrons are there. So you can see here 1s2, 2s2 and 2p1. In one of the 2p orbital there is a one unpaired electron. Similarly, in this boron atom. Okay, so the molecule is having now total 10 electrons. Okay, let us see how the molecular orbitals are formed here. As we know, there is a mixing of the atomic orbitals takes place. Which orbitals are involved into the mixing? 2s and 2pz. Atomic orbitals before the formation of the molecular orbitals. First of all, these atomic orbitals get mixed up, and due to the mixing, what happens? Whatever the molecular orbitals are formed from this, that is from 2s, sigma 2s and sigma star 2s, and from 2pz, sigma 2pz and sigma star 2pz. So due to this mixing of the atomic orbitals, sigma 2s and sigma star 2s having lower energy, their energy level goes down, while sigma 2pz molecular orbital have the rise in the energy level. In oxygen molecule, this sigma 2pz will be here, and this pi 2px and pi 2py will be here. But now there is a change in the energy level of these molecular orbitals. Okay, so sigma 2pz have increase in energy level because of due to the mixing of the atomic orbitals. Hence, pi 2px and pi 2py now having the lower energy level than the sigma 2pz. So thus there is a change in the energy level of the molecular orbitals. And this change can be seen in case of boron, carbon and nitrogen molecule. So let us see what will be happen due to this. So distribute the number of the electrons. Okay. So this 1s, no bonding is there. It will form non-bonding molecular orbitals. Now the 2 electrons will be goes into the sigma 2s. Next 2 electrons will be goes into the sigma 2s, sigma star 2s. And now only 2 electrons are remaining. Okay. If you consider valence electrons 3 plus 3 6. So we have to distribute 6 electrons here, 2 here bonding, anti-bonding. Now 2 electrons are remaining. So pi to px1, pi to py1. So this diagram shows that boron molecule is paramagnetic. This is the new change. And experimental evidences also shows that boron molecule is paramagnetic. Now if we change the energy level of the molecular orbital, suppose that sigma 2pz is here, okay, and pi 2px is here, pi 2px equal to pi 2py. What will be happen? In sigma 2pz, these 2 electrons are paired, so it is diamagnetic. But this is not correct. Actual fact is that the sigma 2pz molecular orbital is having the higher energy level. Therefore, the electrons cannot enter there. The electrons will be entered into the pi 2px and pi 2py. So boron molecule is paramagnetic. Now let us find out the bond order in the boron molecule. So bond order, it is equal to number of bonding electrons minus number of anti-bonding electrons divided by 2. So number of bonding electrons are equal to 4 and number of anti-bonding electrons are 2 divided by 2. So it is equal to 1. So in boron molecule there is a single covalent bond, and that covalent bond, it is a pi bond. There is a pi bond between the 2 boron atoms. Okay. Now, what is the electronic configuration of the boron molecule? So we can write here the electronic configuration of the boron molecule. So you can see here boron molecule. This one is, we have to write K for this one is, K for this one S indicates 2 electrons there. Next orbital, it is sigma 2s. How many electrons? There are 2 electrons. Sigma star 2s also possess 2 electrons. And next it is pi 2px equal to pi 2py. Both are having the 1 electron. And because of due to this, the boron molecule, it is paramagnetic. So the properties of the molecule can be changed, and this change can be explained on the basis of this new concept, that is mixing of atomic orbitals. According to the old concept, we cannot explain this. And experimental evidence shows that boron molecule is paramagnetic, and spectroscopic evidence shows that sigma 2pz molecular orbital is having the higher energy level, and pi 2px and pi 2py molecular orbital, pi bonding molecular orbital is having the lower energy level. So in this way we can explain here the boron molecule. Now let us see the next molecule, carbon molecule. Okay, so this is the hemodiagram of the carbon molecule. Now we know that the electronic configuration of the carbon atom, it is 6. So carbon, let us write here electronic configuration of the carbon atom. So 1s2, 2s2, 2p2. Okay, 1s2, 2s2, 2p2. So there are total 12 electrons in the carbon molecule. Now, in case of the carbon molecule, there is the mixing of the atomic orbital. This mixing of the atomic orbital is takes place because the energy gap between the 2s and 2p is very small. In case of oxygen atom, this mixing is not takes place. In case of oxygen atom, this mixing is not takes place because the energy gap between this 2s and 2p is very large. And in this case, it is very small in case of the carbon. So, due to the mixing of the atomic orbitals, which orbitals are involved into the mixing? 2s and 2pz. So, the molecular orbitals which are formed due to the mixing of the atomic orbitals, their energy level will be changed. And that is represented in this MO diagram. So, you can see now the 1s atomic orbital, 2s and 2p. Now, there are 2 electrons into the 2p orbital of the carbon. Similarly, on this side, atomic orbitals of carbon. Same, 4 electrons are there in the valence shell. Okay. Now, the middle part, it is molecular orbitals. 1s, no bonding, non-bonding molecular orbitals are formed there. Then you can see here 2s atomic orbital of the carbon atom overlaps with 2s atomic orbital of the carbon atom. There is a formation of sigma 2s and sigma star 2s. Now, due to the mixing of the atomic orbital, you can see here these molecular orbitals are having the lower energy level. They goes down. Okay. And the sigma 2pz molecular orbital goes up due to the mixing of the atomic orbitals. Therefore, pi 2px and pi 2py is having the lower energy level than sigma 2pz. So, in carbon molecule, as we know, there are total 12 electrons. So, these 4 electrons are non-bonding. So, 8 electrons we have to distribute in the various molecular orbitals. So, sigma 2s having 2 plus this 2, 4. Now, remaining 4 electrons are goes into the pi 2px and pi 2py, pi bonding molecular orbitals. Now, let us find out the bond order in the carbon molecule. So, bond order, it is equal to number of bonding electrons minus number of anti-bonding electrons. So, number of bonding electrons are equal to 2 plus 4, 6. This 2 plus this 4, 6. Minus anti-bonding electrons are 2 divided by 2. So, it is equal to 4 divided by 2, it is equal to 2. Thus, in carbon molecule, there is a double bond. Carbon-carbon double bond. And these two bonds are pi bonds, okay, not sigma bond. Pi 2px is having 2 electrons, pi 2px is having 2 electrons. So, suppose that this is the pi bond. Similarly, this is another pi bond, pi 2px, pi 2py. So, the MO diagram shows that carbon molecule is diamagnetic because all the electrons are paired. And according to the previous concept, suppose if sigma 2pz is having the lower energy level, now this is sigma 2pz, then pi 2px equal to pi 2py, it is having the higher energy level as per the old concept in case of oxygen molecule. Then the electrons can be filled here. These 4 electrons, 2 electrons will be goes to here and 2 will be here. It means that carbon molecule, it is a paramagnetic, but that is not the real fact. Because in carbon molecule, there is a mixing of the atomic orbital is takes place between 2s and 2pz. Hence, the energy of the sigma 2s and sigma star 2s get lowered and the energy of the sigma 2pz get increases. So, pi 2px and pi 2py come first. Okay. So, let us write now the electronic configuration of the carbon molecule. So, carbon molecule, it is equal to K for this 1s, K for this 1s, that is known to us now. Then sigma 2s, 2 electrons, sigma star 2s2, it also carry 2 electrons. Then pi 2px equal to pi 2py. Both are having the 2 electrons. Okay. So, this is the electronic configuration of the carbon molecule. So, the MO diagram shows that carbon molecule is diamagnetic. It is not paramagnetic. So, this is the MO diagram of the carbon molecule on the basis of mixing of atomic orbitals. So, here this is the main change which is takes place here. The sigma 2pz, it is having higher energy. Due to that, pi 2px and pi 2py, it is having the lower energy. Okay, so the properties of the molecule can be changed. Let us see now the next molecule, that is nitrogen molecule. This is the MO diagram of the nitrogen molecule. So let us write here the electronic configuration of the nitrogen atom. Electronic configuration of the nitrogen atom. Nitrogen is having the atomic number 7. So it is having 1s2, 2s2, 2p3. So in nitrogen molecule there are total 14 electrons. Okay. B2 molecule total 10 electrons. C2 molecule total 12 electrons. Now N2 molecule is having total 14 electrons. In the same way, we can explain here the MO diagram. Okay, atomic orbitals of nitrogen, and molecular orbitals of nitrogen. The diagram is same now. Okay, the same thing will be here. So as compared to the carbon molecule, now 2 electrons are more in the nitrogen molecule. So that 2 electrons will be goes into the sigma 2p side. Next molecular orbital. So the bond order now. Bond order in the nitrogen molecule. Number of bonding electrons. It is equal to 2 plus this 4 plus this 2. So 8. Number of antibonding electrons. This 2. Only 2 antibonding electrons are there divided by 2. So it is equal to 3. It means that in nitrogen molecule there is a triple bond. Triple bond between the two nitrogen atoms. Where one bond it is a sigma bond and two bonds are the pi bonds. This is one pi bond, this is another pi bond, and this is one sigma bond. So in nitrogen molecule there is a triple bond. So nitrogen molecule is a very stable molecule. Okay. Now the MO diagram shows that all the electrons are paired. Hence nitrogen molecule it is diamagnetic. We can write the electronic configuration of the nitrogen molecule. So nitrogen molecule it is having the electronic configuration K, K, then sigma 2s2, sigma star 2s2, then pi 2px 2 electrons, pi 2py 2 electrons, and sigma 2pz 2 electrons. So this is the electronic configuration of the nitrogen molecule. So in this way we explain here these three molecules. So let us take the another screen here. So boron molecule, let us write total electrons 10. Okay, then bond order it is 1. Then magnetic behavior, we can write here the magnetic behavior of the boron molecule. So its magnetic behavior is paramagnetic. It is paramagnetic. Okay. Then its electronic configuration it is electronic configuration according to the new concept. Electronic configuration it is K, K, sigma 2s2, sigma star 2s2, then pi 2p x 1 and pi 2p y1. Okay. So total electrons are equal to 10, 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. So it is paramagnetic. Next C2 molecule. Total electrons are 12. Bond order is 2. Magnetic behavior is diamagnetic. Okay. And electronic configuration it is K, K, sigma 2s2, sigma star 2s2, Then now that two electrons are goes to this pi to px. So we can write here pi to px 2 and pi to py 2. So all the electrons are paired, therefore it is diamagnetic. So in carbon molecule, you can see there are two pi bonds. There are two pi bonds. This one, this second. Okay. Next molecule, nitrogen molecule. Total number of electrons are equal to 14. Bond order it is 3. It is diamagnetic. Nitrogen molecule is also diamagnetic molecule. And its electronic configuration it is K sigma 2s2 sigma star 2s2 pi to px 2 pi to py2 and sigma to pz2. Okay. So in nitrogen molecule there is a triple bond where one it is a sigma bond, this, and two are the pi bonds. So in this way we explain here the molecular orbitals in boron, nitrogen, boron, carbon and nitrogen molecule. Okay. Boron, nitrogen and carbon molecule. So these are the bond orders as we have already calculated in these molecules. According to their electronic configuration also you can calculate the bond order. Just like the electronic configuration is given here for boron. Okay. So you can count the number of the electrons according to this also. These are the 2 plus this 2, 4 bonding electrons minus this 2 anti-bonding divided by 2. Bond order is 1. And that bond may be the pi bond because electrons are present into the pi bonding molecular orbital. Similarly for carbon and similarly for nitrogen. So in this way we explain the molecular orbitals in boron, carbon and nitrogen molecule. So according to the new concept, that is mixing of the atomic orbitals, the molecular orbitals in these three molecules can be explained, where the bond order in the boron molecule it is 1, bond order in the carbon molecule it is 2, and bond order in the nitrogen molecule it is 3. So this type of the change is observed in case of these molecules. The reason is that the energy gap between the 2s and 2p atomic orbital in these atoms is very small. You can see this slide here. See, in case of the boron, that energy gap it is only 449 between the 2s and 2p atomic orbital. In carbon it is 510. In nitrogen it is 517. Now see here, in case of oxygen, this energy gap 1430, very large. In fluorine 1970. Hence the molecular orbital diagram of these three molecules are different than oxygen and fluorine molecule. In oxygen and fluorine molecule there is a no mixing of the atomic orbital, while in boron, carbon and nitrogen molecule there is a mixing of the atomic orbital. And due to that mixing of the atomic orbitals, some molecular orbitals goes down, their energy level will be decreases, their energy level get lowered, while the energies of sigma 2pz and sigma star 2pz are raised up. Okay, that is the main reason why the MO diagrams are changed. So when you draw the MO diagram of boron, carbon and nitrogen molecule, that MO diagrams are totally different than the oxygen molecule. I would like to show here the MO diagram of the oxygen molecule here. You can see the MO diagram of the oxygen molecule. In case of the oxygen molecule, sigma 2pz, it is at the lower energy level than pi 2px and pi 2py. But in case of boron molecule or carbon molecule, the sigma 2pz is having the higher energy level than pi 2px and pi 2py. So this is the very important change in case of the B2C2 and N2 molecule, and whatever the properties of these three molecules can be correctly explained on the basis of this MO diagram. So thus in this lecture we has been discussed the formation of molecular orbitals, in boron, carbon and nitrogen molecule.